Hello everyone, and welcome. In this video, we'll be diving into the world of Power BI, focusing specifically on one of the most important concepts, performance optimization. This session is brought to you by ZoomInData, your space for learning business intelligence and data analytics. So, let's get started and understand how Power BI connects to different data sources and why this process is so essential in today's data-driven world. First question: what factors contribute most to a large Power BI dataset size? Number of rows and columns. Larger tables with many rows or columns naturally consume more memory. High cardinality columns. Columns with many unique values, particularly increased dataset size. Data types. Text columns occupy more memory than numeric or Boolean columns. Date or time columns also add size if auto-generated. Calculated columns and tables. Excessive use of calculated columns increases memory because each calculation is stored in the model. Redundant or unused data. Keeping unnecessary columns, tables, or repeated data inflates the dataset unnecessarily. Second question: why are numeric columns more efficient than text columns in VertiPack compression? Better compression. Numeric columns allow VertiPack to use highly efficient encoding techniques like bit packing, dictionary encoding, and run-length encoding. Lower cardinality impact. Numeric data typically has lower cardinality compared to text, which reduces storage requirements. Faster calculations. Aggregations and measures on numeric columns are computationally faster than text-based operations. Optimized memory footprint. VertiPack stores numeric data more compactly, saving RAM and improving query performance. Third question: what is cardinality and how does it affect model size in Power BI? Cardinality refers to the number of unique values in a column. High cardinality means many distinct values. Low cardinality means fewer distinct values. Impact on compression. Columns with high cardinality compress poorly, taking more memory, while low cardinality columns compress efficiently. Performance effect. High cardinality columns increase storage and slow down filtering, grouping, and aggregation operations. Optimization approach. Replace high cardinality text columns with numeric keys or group values to reduce memory usage. Fourth question: if your dataset is 2 GB and must be reduced to under 400 MB, what steps would you take? Remove unnecessary columns and tables. Keep only data required for analysis. Eliminate intermediate or redundant tables. Reduce column cardinality. Replace high cardinality text with numeric keys or categories. Combine low-value categories. Optimize data types. Convert decimals to integers where possible. Use smaller numeric types. Avoid excessive precision. Push calculations to source or Power Query. Perform transformations outside the model instead of calculated columns in DAX. Disable auto date or time. Prevent automatic hidden date tables for every date column, reducing model size. Fifth question: you have a table with 10 million rows and many string columns. How do you optimize it? Use surrogate keys. Replace text columns with integer keys to reduce memory usage. Create lookup tables. Move repetitive string values to dimension tables and reference them in the fact table. Aggregate data. Summarize data at the required granularity if detailed rows are not required. Remove unused columns. Only retain necessary string columns for analysis. Sixth question: How would you compress a text column with 5 million unique values? Apply dictionary encoding. VertiPack automatically creates a dictionary of unique values for storage. Smaller dictionaries reduce memory. Use surrogate numeric keys. Replace text with integers and maintain a lookup table for mapping. Reduce granularity if possible. Combine rare or less important values into a single category. Consider splitting text into multiple columns. Store only meaningful parts of text in separate columns for better compression. 7th question. Explain how using calculated tables versus Power Query affects model size. Calculated tables in DAX, stored in the model, adding memory usage. They increase model size because the data is materialized. Power Query transformations, performed during data load, so unnecessary data can be filtered out before loading into the model, saving memory. Efficiency. Power Query allows row and column filtering, type conversion, and aggregation before the model sees the data. Best practice. Prefer Power Query over calculated tables for large datasets to reduce in-memory footprint. 8th question. What is dictionary encoding, and how does Power BI leverage it for reducing model size? Dictionary encoding replaces repeated values in a column with numeric indexes referencing a dictionary of unique values. Memory efficiency. Only the dictionary and indexes are stored, which consumes much less memory than storing the original text repeatedly. Applied automatically, VertiPack applies dictionary encoding to text and low-cardinality numeric columns during data load. Performance improvement. Reduces RAM usage, improves query speed, and enhances compression in large datasets. 9th question. What is auto-date or time in Power BI? Auto-date or time is a feature in Power BI Desktop that automatically generates hidden date tables for every date column in the dataset. It allows users to use time intelligence DAX functions, like total YTD, dates YTD, same period last year, without manually creating a separate date table. Each hidden table includes a full date hierarchy, year, quarter, month, day, to simplify reporting and drill down analysis. The feature is enabled by default, but it can be disabled in Power BI options to improve model performance. 10th question. Why does Power BI create hidden date tables automatically? To simplify time-based calculations and allow beginners to perform time intelligence without additional setup. Ensures that DAX time intelligence functions work correctly for each date column automatically. Provides pre-built date hierarchies for easy visualizations and drill-down capabilities. Each hidden table is associated with its date column, but in large models, these multiple hidden tables can increase memory usage and model complexity. 11th question. Why is auto-date or time considered a performance issue? Every date column generates a hidden table, which increases memory usage and enlarges the dataset unnecessarily. Queries must navigate these hidden tables, which slows down report rendering and DAX calculations, especially with multiple date columns. Automatic relationships between hidden tables and fact tables can increase calculation complexity and impact performance. In large models with multiple date columns, refresh times are longer because more metadata and relationships need processing. 12th question. Your model uses 20 date columns. How does auto-date or time impact memory? Each of the 20 date columns creates its own hidden date table, multiplying memory usage and increasing dataset size. VertiPack stores these hidden tables in memory, leading to significant memory consumption. Queries accessing multiple date columns must also process all associated hidden tables, which can degrade report performance. The increased model size may also slow down visual loading, refreshes, and interactions on the report page. 13th question. Auto-date or time is disabled but time intelligence still fails. Why? Disabling auto-date or time requires a custom date table to be created and marked as the official date table in Power BI. If a date table is missing or not correctly marked, DAX time intelligence functions, like total YTD or same period last year, cannot identify the proper date hierarchy, causing errors. Relationships between the date table and fact tables must be active. Otherwise, calculations fail. Using inactive relationships without applying use relationship also prevents correct time intelligence calculation. 14th question. When is auto-date or time useful, and when should it always be avoided? Useful in small datasets with only a few date columns, for quick prototyping, dashboards, or when beginner users need simple time intelligence. Avoided in large models with multiple date columns, because it significantly increases memory usage and slows report performance. Best practice: always create a single, custom date table to handle all date columns, ensuring consistent hierarchies and better performance. Custom date tables provide control over fiscal calendars, special dates, and time intelligence while reducing model complexity. 15th question. Why do aggregations improve performance in Power BI? Aggregation tables store pre-calculated summary data at a higher granularity, example monthly or regional totals, reducing the need to query large fact tables. By querying pre-aggregated data, Power BI reduces memory and CPU usage, speeding up report visuals and DAX calculations. Aggregations are particularly effective in direct query and composite models, where querying the source for millions of rows is slow. They enable efficient fallback mechanisms. If a query can be satisfied by the aggregation table, the engine avoids scanning the detailed fact table entirely. 16th question. What is the difference between import, direct query, and dual storage modes in Power BI? Import mode. Data is loaded into Power BI's in-memory VertiPack engine, providing fast query response but increasing memory usage. Direct query mode. Data remains in the source system, and queries are sent live. Memory usage is low but query performance depends on the source. Dual mode. A table acts as import for aggregations and direct query for detailed queries, allowing Power BI to automatically choose the optimal source based on the visuals fields. Choosing the appropriate mode impacts query speed, refresh strategy, and resource consumption for large datasets. 17th question. How does Power BI decide whether to hit the aggregation table or the detail table? Power BI evaluates whether the fields and granularity in the visual can be satisfied by the aggregation table. If the aggregation table contains all required measures and dimensions at the correct level, the query uses the aggregation table for faster response. If the visual requires fields not in the aggregation, or relationships prevent aggregation usage, Power BI falls back to the detailed fact table. Correct field mapping, granularity, and storage mode configuration are essential for proper aggregation usage. 18th question. Your aggregation table is not being used. How do you troubleshoot it? Check field mappings. Ensure all measures and dimensions in the visual match the aggregation table fields. Verify granularity. The aggregation table must meet or exceed the granularity needed for the visual. Check relationships and storage mode. Aggregation table should be in import mode, and relationships must be active and correct. Use the View Aggregations or Performance Analyzer tools to see if queries are eligible to use aggregation tables. 19th question. How do you design aggregations for a 500M row direct query fact table? Identify frequently queried metrics. Focus on commonly used measures like sum, count, max, and min for pre-aggregation. Create aggregation tables in import mode. Store summaries at higher granularity, such as by month, region, or product. Map aggregations to detailed measures. Use the Manage Aggregations feature to define which measures and columns the aggregation supports. Keep a direct query table for detail-level queries. Allows fallback to detailed rows when needed while still leveraging fast aggregation queries. 20th question. What are the limitations of aggregations in composite models? Aggregations cannot satisfy queries that require unaggregated fields not present in the aggregation table. Using row-level security, RLS, can complicate aggregation usage. Filters must align with aggregation structure. Only certain storage modes and sources support aggregation tables in composite models. Misconfigured aggregations can cause queries to fall back to the detailed fact table, reducing performance benefits. 21st question. What is incremental refresh in Power BI, and why is it important? Incremental refresh is a Power BI feature that refreshes only the latest or changed partitions of a dataset rather than the entire dataset. It is particularly useful for large tables with millions of rows, as full refreshes can be time-consuming and resource-intensive. Historical data partitions remain static, which reduces processing time and memory usage during refresh. Incremental refresh ensures faster report updates and improved performance for enterprise-scale datasets. 22nd question. What are range start and range end parameters, and why are they required in incremental refresh? Range start and range end are Power Query parameters used to define the time window for each partition in the dataset. They are applied in the filter on the date column, allowing Power BI to process only the relevant subset of data during refresh. Proper use of these parameters ensures query folding, so only necessary rows are fetched from the source. Without range start and range end, Power BI cannot create partitions or implement incremental refresh, and the entire dataset would refresh every time. 23rd question. Your refresh is still slow even after using incremental refresh. What steps would you take? Ensure the data source is optimized, such as creating indexes on date columns or reducing unnecessary joins in SQL queries. Limit the archive period or reduce the refresh window to process fewer rows per refresh. Confirm that query folding is applied. Transformations must be folded to the source for efficiency. Consider hybrid tables, import plus direct query, to combine fast partitioned refresh with real-time latest data. Check on-premises gateway performance if using on-premises sources, as it can become a bottleneck. 24th question. Incremental refresh shows no partitions after publishing. What could be the reasons? The data source does not support query folding, preventing partition creation. Range start or range end parameters are not correctly applied in the Power Query filter on the date column. The dataset has not been refreshed yet in Power BI service. partitions are only created after the first refresh. Tables set to direct query only mode cannot create import-based partitions, which is required for incremental refresh. 25th question. When should you enable Get the latest data with direct query in incremental refresh? Enable it when you require real-time or near real-time updates for the latest partition in your dataset. Ensures that recently added or modified data is always queried from the source instead of relying solely on import partitions. Useful for dashboards that need up-to-date metrics daily or hourly without refreshing the entire dataset. Works best with smaller incremental partitions to avoid performance degradation. 26th question. How do you validate that partitions were created correctly after configuring incremental refresh? Open the Power BI service, go to the dataset, open the refresh history, and check the partition information to confirm that partitions have been created. Verify that the range start and range end parameters are correctly applied for every partition that appears in the dataset. Check that only the incremental partition is refreshing during scheduled refresh, while the historical partitions remain unchanged. Use DAX queries, database logs, or the performance analyzer to confirm that the queries are targeting the correct partitions during the refresh process. 27th question. What do the DAX query, visual display, and other timers represent in Performance Analyzer? DAX query measures the time Power BI takes to execute the DAX query against the model and retrieve data for the visual. This reflects the computational performance of measures and filters. Visual display measures the time it takes for the visual to render on the report page after the data is retrieved. This is affected by visual type, number of points, and formatting complexity. Other includes time consumed by interactions, layout calculations, and background operations such as bookmarks or slicer actions that are not DAX or rendering. Understanding these timers helps pinpoint bottlenecks, whether the slowness is due to DAX calculations, visual complexity, or other report processes. 28th question. A visual takes 6 seconds to load. How do you troubleshoot it end-to-end using Performance Analyzer? Step 1. Check the DAX query time in the Performance Analyzer to see whether the query execution is slow. If it is slow, optimize the measures, reduce the number of calculated columns, or simplify the filters that the visual is using. Step 2. Check the visual display time. If the DAX query is fast but the visual still loads slowly, investigate the visual type, the number of data points, and the level of formatting. You can also switch complex visuals to simpler charts or aggregate the data. Step 3. Check the time shown under the section named Other. Look for slices, conditional formatting, bookmarks, or interactions that may be causing the page to load more slowly. Step 4. Apply improvements one by one, then refresh the Performance Analyzer and compare the times to confirm that performance is improving. 29th question. Your DAX query time is fast but visual display time is slow. Why? The visual contains too many data points, e.g., large tables, scatter plots, maps, which increases rendering time. Complex conditional formatting, tooltips, or custom visuals can significantly slow down the display. Page design and overlapping visuals may require extra processing, delaying rendering. Optimization may involve aggregating data, simplifying visuals, or limiting the number of slices and filters applied. 30th question. How do you use Performance Analyzer and DAX Studio together for report optimization? Use Performance Analyzer in Power BI to capture slow visuals and the DAX queries. Copy the DAX queries into DAX Studio to analyze them further using query plan, server timings, and VertiPack engine metrics. Identify bottlenecks in calculations, filter context, or storage engine operations. Apply optimizations such as rewriting measures, reducing table size, or using aggregations, and then retest using Performance Analyzer. 31st question. The first load of a report is slow but subsequent loads are fast. Why? The first load involves query compilation, cache creation, and initial data retrieval, which consumes time. After the first load, Power BI caches query results and visual data, so subsequent visual loads are faster. This behavior is normal for large datasets and complex models, where initial memory allocation and calculations are significant. Performance can be further optimized by preloading data or using aggregations to reduce initial query processing. 32nd question. How can you detect inefficient relationships using Performance Analyzer? Long DAX query times for simple visuals may indicate inefficient relationships. Example: many-to-many or unnecessary relationships. Check relationships between tables that are used in visuals with slow query performance. Using Performance Analyzer, track which fields or tables are contributing to delays and consider restructuring relationships or using composite models. Optimize by removing unnecessary relationships, enabling single-direction filtering, or using star schema design to improve query speed. Thank you for watching this session. If you have any questions, you are welcome to contact ZoomInData through our website, email, or phone. We're always here to support your learning journey. See you in the next video.